Okay.
Good. So last 2 days we talked more about simulation techniques. On Tuesday, gravity. Yesterday, a bit more on hydrodynamics. Today we're going to go back a bit to galaxy formation and a bit more on the theory side for the first half, and for the second half, I'll try to describe a bit how we can do some of these processes of galaxy formation inside the simulation. That's a topic for about 6 months worth of lecture. So we'll do, it's going to be very superficial today. Of course, we can talk about it more. If you have questions or anything, feel free to ask, and I can talk more about some of the details that you may be more interested in. Okay, so let's see what is. Yes, okay. So here we are, just summary where we are this week. So, galaxy formation theory and simulation this morning. This afternoon, we'll see either we can continue a bit what we did yesterday. I think some of you were close to getting some results, so maybe we just want to finish that. And otherwise, I have some simulations that have already been running a bit, and we will be using, I have some small simulations with galaxies in them. We're going to be running for a bit and then we're looking at some of the results. We either run them or just download the results and start looking at them. We'll see how it exactly goes. And then tomorrow we'll be discussing a few more modern topics. I'll be talking maybe more about more up-to-date research, kind of things we do in my group, and then maybe the future of what's going on. Are there any remaining questions or anything about yesterday or the days before? Anything you would like to ask, talk about? Yes.
When you try to derive the Euler equations, you are doing it from an inertial reference system.
Yes.
It would be the same if the fluid was in a rotating system or a non-inertial frame.
Yes, you could rederive the whole equation in a different frame if you wanted. I don't know why you would want to do this. Do you have a special scenario in mind? Something? Why would something that you would use?
Or something else.
Yeah, so I mean, there are, I guess, yes, you could construct special cases where you have some motion being removed or some special frame. Sometimes people also work in spherical coordinates. For instance, if you're simulating a single star or indeed the whole atmosphere. But usually you don't, people just do the simplest derivation possible and let the computer do all the work rather than this. Good. Okay, so to pick today, as I said, probably 6 months worth of lectures in an hour. Talking about how galaxies form, and so we stopped on Monday and sort of Tuesday about discussing how from gravity you can start collapsing into structures. We looked at how in simulation were showing us the filaments and also some halos. We can sort of start where we left off and then assume that we somehow through gravity we understood how we can construct halos, and then from here on see how we can go and whether we can form galaxies, and what are the processes that are relevant for galaxy formation onwards. Okay, so that should be working today. It's on this machine. So we're going to start again with a movie to put us back into the spirit where we are. let's try this one. Doesn't like doing videos from this machine somehow. Okay, that's not great. It's telling me it's impossible to read the movie, which is not good. Yes, this one is. It's just different, different screen. No? Okay. That's for a second try something different because I have it on my laptop without internet. So
I feel it was in
this.
No.
Give me 1 second. Okay, here I have it outside the internet. Okay, so let me start again. We'll switch back to the presentation in a minute. Okay, so what are we looking at here? So we can think of this as being the state of where we left on Monday. So we're looking here at the region of the universe. So this is about. So I showed you a movie where we're zooming into a galaxy and we're looking at how the disk is forming. Here we're not going to do any zooming at all. All we're doing here is just looking at the large scale structure. I'm going to just switch off the light. Second. So what we're looking at here is the large scale structure. So it's a 25 megaparsec region. What you have here is color. So what I've done in this movie is coloring the gas. So we're only looking at the gas, but the same kind of filament and halo structure will form. The more intense the color is, the denser it is, right? So here we have a region which is very empty, which would be like the void, and then we have filaments, and then we will start to see halos forming where the filaments meet. There's redshift on the left here. If you prefer time since the Big Bang, it's also given down there, and then the color corresponds to the temperature. So if it's dark red, it's cold, which means 10 million Kelvin. It's cold for galaxy formation people. And if it's white, it's going to go maybe to 10, so what did I say, 10,000 Kelvin? Yeah, 10,000 Kelvin for the dark red. It's going to go to 10 million Kelvin for the white part, okay? So what you guys see, so we're going to be moving around a bit in the simulation and see how that region is. So let me put it back at the start. Okay, so as we expect, for now at redshift, that's redshift 20. Right, so 200 million years after the Big Bang, it's still very, very uniform. You can see it's very relatively boring, very almost uniform density still, and also uniform temperature. Okay, so I can start playing it again. So the rotation is not the real rotation of the universe. It's just it looks cool in the movie to give us some different perspective. Right, the whole universe doesn't have a sort of angular momentum rotation thingy. So you can see like now we're redshift 5. You can see now in the center here of these, where the filaments meet, we are forming denser region, but also we are forming bubbles, right? So this is, we're not looking at the galaxies are too small, we don't see them, they will be less than a pixel on the image, but we're looking at the center, these halos, these galaxies are forming. In the galaxies, stars are born. There are also black holes, maybe a supermassive black hole in the center. These stars, they take their life and then they explode in supernova, and then that will create bubbles of hot gas that is being expelled outside, maybe out of the halos. Now we have, redshift 0.2 is almost present day. Now you can really clearly see this set of filaments, right, and very, very empty region in between. We have very big black void, where there is very little gas, the filaments, and then in the middle, where the filaments meet, again, these halos, and inside the halos, the galaxies, and the galaxies create these bubbles. Shall I take one more? Yes. So here I'm only showing the gas, but the dark matter is doing pretty much the same thing. The gas is subdominant, it's only 20% of the mass over the dark matter, so you can think of the dark matter creating filaments, and the gas is following because of gravity. You can see that the explosions, there's sort of constant flux. You get like episodes of bursts of hot gas coming out of these galaxies. Of course, that's a simulation to a given model. It may not be entirely correct. Hopefully, it's not too wrong. But that's, we can't. This is 13 billion years of evolution, so we can't actually observe all this detail. And so, just to give a sense of scale, maybe these sort of intermediate size blobs here, there would be a halo like the Milky Way, where we live. So that would be our kind of galaxy size that we have. The slightly bigger ones would be some of the group of galaxies, and so on. So this is not a very big region, so we don't have any clusters in there, but it would be an even bigger scale. Okay? All right, so I'll try to go back to the slides which are on here. Put back some lights. Good. So the second movie was pretty much the same thing, so I'm just going to skip that because it's problematic enough. Okay, so if I just take a still image from one of these region of the universe, so this is from another simulation, that doesn't really matter. What we have, again, we have these filaments, and then the key tool that a lot of the models rely on, and we also discussed already, we already played around with some halos merging on Monday in the simulation session, is that, again, these filaments, and then you have different halos. What you can see here, so this is now showing the dark matter, is that you have these spherical regions that have collapsed, and then in there, these are the highest density regions in the universe. And so if we think from where we want to go, these are the regions where it's the highest density of dark matter, also the highest density of gas, and this is where there will be enough material in a small region to start forming galaxies. So maybe the first step in getting towards forming galaxies will be to understand a bit the population of these halos, so that we can start looking at what happens in them next. So the first thing we can ask is, okay, so we can see dense regions of images, but the first thing we can say is, okay, how do we even define it? Where are the halos? What are the halos? How do we even define all these things? And so astronomers love to use dark matter halos, again, because they are very simple objects that we can then use to start constructing the rest of the theory on. But there are things that are very badly defined. Like me, if I give you an image, people can pinpoint say, here's a halo here, there's a halo here, there's a halo here. But then, if you start asking questions like, what is the edge, where does the halo stop, what is exactly the center, what is the halo mass, there are like definitions where things can vary by a factor of a few, depending on who you ask and how you want to measure things. So typically, people will define something like a virial radius, which could be the idea of this is the region of the halo which is dominated by its own gravity. So all of the objects in there are virialized, and they follow the Virial theorem. And so the particles or the galaxies or the gas in there is nicely orbiting and well behaved. But some other people prefer to define something like a splashback radius, which would be something like Sometimes you can have a galaxy that, so you have a halo here, you have a galaxy coming from very far away, it comes in, right? It goes down the potential well, and will come out on the other side, and then will turn back and come back in. So you can calculate what is the furthest distance that something could come back out and plunge back in. That would be another definition of what is the halo edge. And then also people like to define halo, maybe halo radii by a certain threshold. So if this region has a higher density than X, then that is a halo with a given size, right? So, for instance, and that's probably this last one is the most common definition, is that people like to define the halo edge and the mass by some sort of average density within a region. Define something like the mass of the halo, the very mass of the halo would be some spherical radius, r cubed times an over density definition. So for instance, you will say something like, I want my regions to be 200 times the critical density of the universe. And critical density is defined by cosmological parameters. It's defined by 3h squared over 8 pi g. So that's just defined by cosmology. So I can say, I'm going to define any region which is 200 times more dense than the critical density as a halo. I'm going to throw a sphere around these regions, and that's going to be my definition of a halo. Right? Some people, for instance, if you talk to people who do X-ray astronomy, because it's very difficult to see the outskirts of a halo, they prefer working with something like 500 here, which is a smaller region, but it's a denser region. If the gas is denser, it will be emitting more X-ray lights. So that's a much more appropriate definition for them, for instance. Okay, so we have some sort of a tool where we can sort of define what a halo is. And then one thing that you may have tried to plot on Tuesday afternoon from simulation was the halo mass function, which is the number of halos as a function of the mass. It's just simple statistics. I have a region of the universe. How many halos are there that have a certain mass? So I'll ask you on Tuesday, what is the halo mass of the Milky Way? Let's see whether we have another answer today. Any volunteers? Still a volunteer. Okay, so the halo mass of the Milky Way where we live is about 10 to the 12. Okay? If you go this way, we're talking about sort of dwarf galaxy regime. 13 to 14 people will call these galaxy groups because there are like 2 or 3 galaxies in that single halo. And then we're really talking about clusters when we go to the very massive end. So what this plot is showing here is, again, simple statistics. So how many halos of a given mass there are per unit volume of the universe. So it's a number density. And then the different colors here show you the evolution. So of course at very high redshift, there are very, very few structures. If I go to redshift 10, like this yellow, green, horrible color here, then there are only, there are no big halos because there's not been enough time for big structures to collapse anymore. But then you can see that as time passes, the structures grow, and then you get more and more. So you get bigger halos, first of all, so it moves to the right, but you also get many, many more. Okay? So you can, and then the classic thing, so the key part here is that this slope here is sort of mass to the -1, and there's an exponential break. Yes?
And they're not supposed to be like a constant when this pass too much time. Well, I mean, the universe are expanding, how I can get a bigger halo if my matter is already far, far away. You know what I mean?
So, yeah, so if you make the Hubble constant much, much larger, and the universe is expanding enormously, then the halos will stop growing. But we're not there yet.
Okay.
Right? So at the moment, gravity is still winning over lambda. So we are still having our halos grow with time.
Okay.
But the fact that there's this connection between the number of halos and the cosmological parameters. And so that actually, if you could measure this very precisely, you could also measure the cosmological parameters. Because if I make a change to lambda, or make a change to omega matter, the shape of this will also change. So maybe one of the interesting things, what is going on these days, you may have seen, so the JWST satellite was launched a year and a half ago, and they were starting to take data and measuring galaxies, and there's a lot of excitement because people were finding, or they think they are finding, big galaxies at high redshift. So one problem you can have, if you find a very big galaxy at redshift, say 10, and you find a big galaxy here, but that's a galaxy, right? So you're measuring the stellar mass, but the galaxy probably lives in a halo or something. But even if you find a very big galaxy here, you could say, well, but that's a problem because there are no halos that are big enough to have that galaxy in it. So if you find a very, very big galaxy at very early times, that's a problem for the lambda CDM model, because how do we even put that galaxy in a halo if there are no halos which are massive enough? So that's coming as an alternative because measuring stellar mass is very hard, and even measuring the redshift of this object is not straightforward. But there are some debates in the literature over the last year whether we have a problem or not with some of the early observations. Okay. No, that's not wrong computer. Okay, just a side question. So look at all of these halos. Now, if I ask you, what is the halo mass where most of the mass is? So we have all of these halos, with halos that are 10 to the 15, so they're really big. These halos here are 10,000 times or 100,000 times lighter. Right? But there are also more of these guys than there are of these guys. So what is the halo mass where most of the dark matter mass is? Yeah, 10 to the 11, another guess? No, it's more than that. It's like slightly, so if you take that and you integrate under the curve, and you ask, right, the curve it's always log, so it's very confusing. So the peak is around 10 to the 13. So that's where most of the mass in dark matter inside halo is in this. The smaller halos, they are too light to contribute much. And the big halos, they are more massive, of course, but they are too rare to contribute much. There is sort of a peak between 10 to the 12 and 10 to the 13 as to where most of the mass is. And we happen to live in a 10 to the 12 here, so we're close to the sort of most likely region to be in.
That's for
That's for redshift 0. Yes. That's not redshift 0. You can do the same thing for all the redshift, but this specific one is redshift 0. And of course, yes, that mass changes with time. Okay. So now the other thing is that we played around also on Monday in the simulation. We try to make two halos merge. Now, of course, you could see also in the simulation we start with something very uniform, and then the regions grow, but they also the small halos merge into the bigger halos, so they fall into bigger halos. That's a famous plot, although it's very strange for a plot of itself. It's a famous plot from a paper from 1993. We introduced the concept of merger trees. Because if you think all of the small halos, they're like the leaf of a tree, and then they make the branches, and they make the bigger branches, and then they go back to the trunk, right? So a big halo at the end, by redshift 0, is probably made of all of these small halos that over time have collapsed with each other, and they're forming the bigger and bigger structure. And that's a feature of cold dark matter, that we first form small structures, and then they collapse and get bigger and bigger. So you should expect to see small galaxies early on that become bigger and bigger. Small halos and also small halos. And so what people do from the simulation as well is that once you have all of the halos at all of different times, you can actually go in the simulation, connect them through time, and construct these merger trees. You can see how every object has formed over time. That's, of course, you can only do in the simulation. You can do this into the data, but that would be something that is a very common practice. Another way of looking at this is sort of very similar, just a different view instead of drawing sort of baobab trees, to draw something like that, where you have different halos merging at different times and collapsing into the bigger and bigger structure. So you can look at different slices in time. So for instance, the Milky Way is very close to the Andromeda Galaxy. Right? And so we know, by just measuring the dynamics of these two objects, that in about 4 or 5 billion years, the two galaxies will merge and will be in a single halo that contains, well, that both galaxies will be merging, but also the two halos that contain these galaxies will merge. The Milky Way itself hasn't had any big merging in a long time. If you look at the Large Magellanic Cloud or the Small Magellanic Cloud, these are small satellite galaxies that have fall into the potential well, and they are coming into the galaxy. And so we know to the case where we have two halos of the same size, it would be something like the Milky Way is sort of 10 to the 12, and the Magellanic Cloud maybe 10 to the 10. So there's a factor of 100 different, but it's still the same process. Small things are merging into the bigger things to form bigger and bigger halos. Okay, so here's just a fun maybe question just to see where we are at. So we can measure the halo masses in the simulation. So that would be the red line here. Okay, so I can go and say, this is how many halos with a given mass I have. That's the picture I had before. And what I can do, I can say, I'm going to simplify things. I'm going to say, in every halo, I know what is the Darwin fraction. So we know that 20% of 80% dark matter. So if I say, I make an extreme scenario where I take all of the mass, or all of the gas mass in the halo, and I turn it into stars. Everything. There's no gas left. Every single gas in the halo turns into stars. Okay? That's the maximal efficiency you can do. Of course, that's the extreme scenario. Right? That's not how it works, but it's just the most extreme thing you could do. And that gives us this red line here. Okay, so it has this specific shape, and the specific just rescaling the curve I had in the previous one. I'm just turning 20% of all of my matter in halos into stars. So now what I have here is not a halo mass, sorry, on the x-axis, but it's a stellar mass. It will be sort of the mass of the galaxy in each of these halos, where I've turned 20% of the mass. Now what I can do is I can go in the data and get this blue line, which is the real observations. This is the number of galaxies of a given mass per unit volume of the universe. So this is what my theory prediction is, and this is what the data wants. Okay, that's an extreme theory, right? But there are two important things. One is, first of all, the data is never, of course, the data is never exactly on the line, because it was an extreme scenario where I made everything turn into stars. So of course the universe doesn't do this, which is a good result here. But the important part here is that the shape is different. So the blue curve is more flat, and then also it's much more steep here. Okay? Do you have a suggestion as to what is going on here? Apart from that model being way too simple. So why is my model too simple? What am I missing? Okay, so the key thing is that this efficiency saying everything turns into stars at 100% rate, that's wrong, but that was just the normalization here. But also, it's telling us that it's not just a fixed fraction. Right? Some halos, the small halos, are much less efficient at forming stars. The distance here between the blue and the red line is much larger, and so are the big halos. And there are these halos here that seem very efficient compared to the rest. They seem to be the best halos at forming stars. If you take all of them, they're. And so then, what people think, and that is sort of working from theory and simulation, is that there are two main processes that make this happen. Okay, that should be a bit. So on this side, we think it's due to the feedback from AGN, so the supermassive black hole at the center of the galaxy, in these really big galaxies, prevents more star from forming. So the halo keeps growing, but that black hole in the center injects so much energy into the system. Remember these big bubbles we were seeing in the simulation before? That is stopping because it's injecting a lot of hot gas. It's preventing the galaxy from forming more stars. So we stop forming stars, but the halo keeps growing. And on the other side, we don't have AGN because these are small galaxies. They don't have a supermassive black hole at the center. We think this is all done due to just the stars exploding. So the stars do the same thing. The stars, they bore for a bit, of course, that otherwise we don't have a galaxy. And then they explode, and by injecting more energy, they stop more stars from forming. And somehow there's a maximum efficiency here, that where this process stops being efficient, and then it's before they already have a big black hole, where the black hole takes over. We can plot this in a slightly different way. We can plot it this way, where now I have the halo mass, again, and this is the ratio. So this would be the ratio of my blue curve from the previous plot divided by the red curve. So that means essentially how close am I to the blue to the red curve? How efficient am I at turning the mass in a halo into stars? And we find there's a peak at around 10 to the 12, which is the mass of the Milky Way. So the galaxy like the Milky Way, like a halo like the Milky Way, is sort of at the peak of efficiency at turning into stars. And so our Milky Way mass halo is about 10 to the 12, and we have about 6 times 10 to the 10 solar masses in stars. So it's about 6% of the total mass of the halo is in stars, which is sort of peak efficiency. And if you go to clusters, then the thing, it's only one. That we are here at 10 to the minus 3, it's a log scale, so it will be only 0.1% of the mass of the halo is into stars. You can see on the other side, it also dies down, and in the same way. Okay, so let's go back to these processes. So we have halos. How do we form? So we have halos, they got their gas. Okay, so how do we now get gas? The first key process that takes place is what we call cooling. And so what we have is this gas is pretty hot because it's in equilibrium with the gravitational potential. So if you want to condense the gas in the center of the halo to make it dense enough that we can start forming stars, we need to remove energy from the system. The gas has too much energy because it's in equilibrium with its potential well. So the only way we can compactify, or you could either compactify by like compressing it from outside, but I don't know how you do that. You can't go out the halo and just compress it. So the only way is to do something internally. So you have to remove energy from the gas to make sure all of the gas comes into the center, right? And so that you can do by removing thermal energy from the system. So that's what we call cooling, and I'll show in a minute what the exact process here is. But you can think of, we start with your dark matter halo, the gas which has the same shape and profile. You cool it down, so the gas particle lose energy, and the only thing they can do is fall into the gravitational potential and get to the center. So we start with dark matter halo, the hot gas is the same thing, but then the gas cools, and then it starts forming a region in the center where we have where we have a cold gas disk. Okay, so that should be a movie, which there may or may not be a chance that it works. We'll never know. Yes, no. Still an error. Let me see. I think I also have this one. Yes. I guess this one is basically enough like that. Thanks. So what we see here, so this is a very simple model. I have not done anything. So all I've done here, this is from the so I've done this. I take the halo with an NFW profile that we've seen in the dark matter on Monday. I put some gas in there, which has a certain just temperature that is there to compensate the gravity. And then I go by hand in a simulation, right? Just magically, and I just cool down. I remove temperature from the gas. It's a simulation, I can do whatever I want. And if all that happens, that's enough, right? It's a very simple thing. I'm not doing any magic. But I'm doing magic by removing energy from nowhere. But apart from that part of magic, all that is happening is that the gas is cooling down and making more and more dense. You can see that's just growing the disk at the center of my head.
You're putting all the gas that is
In the whole head.
all the gas.
All the gas. But then you can, so I'm removing energy, but that will depend on the density, so if it's more effective. The denser something is, the more it will cool. Okay? So this is just showing a very simple process. This is just gravity, gas physics, and a bit of magic removal of energy. Okay, so now a question for you. Why is this thing rotating? Okay, again, I can tell you, first there are two questions. Why is it a disk? And why is it rotating? All I've done is, okay, I start with a halo, I removed energy. So I tell you to go to the center. Right? That, I think that should make sense. Why does it make a disk? Why is it rotating?
It's a disk because it's rotating.
Okay, but that doesn't help.
It's for the conservation of the
Correct. So the key part here is conservation of angular momentum, right? So if I start with a halo, and I just start with a random distribution of particles, there's always going to be a non-zero angular momentum vector. And then by conservation of angular momentum, I will have to keep that motion going, and indeed, because it's rotating, it will indeed form this coordinate equivalent. So key part here, somehow removing thermal energy to conserve angular momentum. Okay. Well, you get a disk. Okay, let's play the same movie again. Convince yourself that it makes a disk. I guess you're convinced. Now the question is, what is U? Okay, so this should work. How and why do we get any cooling working in the first place? How is that? If we want this to work in the real universe, I can't just go magically remove energy. What is the process that removes energy from my halos? Yes. Okay. But from? So you think the hot gas is losing energy from itself because it's hot? Okay. Yeah, that's one process. Is that sufficient? Do you think?
Maybe it's collapsing.
Why? It is collapsing because it's cooling.
It's cooling because it's collapsing.
Okay, so which one happens
to lose energy?
Yeah.
It starts to collapse.
Yes. So the denser you are, you're right. So the more dense you are, the easier it is to lose energy. So there's sort of it gets faster and faster. Yeah. But so you said something about radiation. So there are two things you can think about with radiation. One is indeed, if you have a very hot gas, or any temperature, but mostly hot gas, it will lose energy by just heat, right? Photons going, right? But also you could have photons interacting with the gas and changing the levels of your atoms. Okay? So these are different processes that can take place. And so these are the main ones that we have that are to play role. There are many more, but these are sort of the key ones that play quite different things. So you were thinking something like the Bremsstrahlung at high temperature, so it would be like just the hot gas losing energy in some way. Then you have the emission of photon between different levels of energy. So you have all of these molecules, sorry, not molecules, you have all of these atoms, maybe especially if you have not just helium and hydrogen, but you also have different elements. They can quite easily lose energy by changing level of excitation. If you're already in a situation where you have 4 molecular hydrogen, or any other molecule, you can lose energy by changing the vibration level of the molecules. And something that always works, but is very inefficient, but it always works, and that's sort of starting the process in a way, is that you can do quantum interaction with the CMB. So you always have a flux of CMB photons. Remember we said these photons of the CMB were emitted just after the Big Bang, 300,000 years of the Big Bang, and are flying to us. They are flying through everything, and sometimes they interact with atoms in the way via quantum interaction, and that will also change the energy of the gas. Yes?
In the previous simulation, you centered the video on
the center of the halo.
Center of the halo.
Yes.
Because
I know where the galaxy is.
why is it formed? It is not supposed to be open, it's closed.
Well, in the simulation it was just starting with a potential well. Now in reality what happens is that because the halo is growing, there's more and more stuff also coming in because the halo is growing. But if this was just an isolated system, just showing that cooling and angular momentum is enough to do this. And so this here, this sort of the regime where these things matter, so this is really only at high redshift that it plays a role because other processes dominate after that. This is only in cold regions. This happens for very hot gas, which was your equation before, and this is really the main process that the photon exchanging level and so what people then usually do, and this is all governed by atomic physics. So if I know my nuclear physics, my atomic physics, in quantum physics class, you've probably calculated the hydrogen atom and all the different levels. If you now do this, obviously you can do it by pen and paper, but you can do this for all of the molecules, all of the atoms, then we know exactly what is the level of photons, how much energy can be lost by every level. And so this is all governed entirely by atomic physics. So we know exactly how this works. So there's not much unknown here. And so if you put all of this calculation together, you can sort of have what we call a cooling curve, which if I have the temperature here in log, so going from 10 to the 4 to very hot, and on the y-axis you have the rates, the cooling rates, how much energy is lost per atom in my gas per unit time. Right? And so there are here the different curves correspond to different level of metallicity. So blue is if I only have hydrogen and helium, so which would be the primordial state of the universe. A bit of lithium, but it doesn't matter. And then these are if I now have other elements that are produced by stars. And so that you can see it makes the curve jump by almost an order and a half, 1.5 orders of magnitude. So having extra metals, extra elements is very, very important if you want to speed up the cooling processes. But also there are some specific features, the shape is very important, will play a role as to what can happen in gas. So this is all governed by atomic physics. Okay, so now we have formed the whole disk. Then comes the next step, which will be star formation. So what should happen next? Yes. So now that becomes a bit more complex because we don't have a full picture or full complete theoretical understanding of all of the details of what is happening. So we have the disk. We're gonna in the disk itself. It's not going to be completely uniform, right? There will be regions, and also because of the rotation, there'll be shearing, there'll be maybe spiral arms forming, it will be disrupted into smaller and smaller regions, which we usually call giant molecular clouds. We'll start forming then denser and denser regions. We're going to form molecules, especially H2 molecules, or even denser elements like CO, which is one of the traces people use a lot. So CO, the molecule of carbon and oxygen going together, only forms at high density and cold temperatures. This is one of the molecules when people measure star formation in other galaxies, they go and look for that molecule because it's a tracer. If you have a lot of it, it means you have a lot of cold and dense gas, and you're probably forming a lot of stuff. So that could be one. And so the idea is that you are now forming dense clouds. These dense clouds, there is no doubt, they are again going to collapse under their own weight, and they're going to stop collapsing only until they reach a density where a star can form. So you can think of this as very similar to what we have seen before, where we have a halo, and the gas collapses and forms a disk. And now we have the gas in the disk that collapse and form stars. But there's a key difference here, is that these clouds don't have any dark matter. And so the halo itself was made of dark matter, and the gas collapses inside the potential set by the dark matter. Here, it's just a clump of gas, and it's just collapsing. And there, the details of that are not entirely yet understood. We don't have a full, so we have the global picture that I'm giving you, but we don't have full calculation telling us. But you could imagine one key goal would be to say, if I give you a gas cloud with a given shape and a given mass, and maybe tell you something about the composition in metals, in elements in there, I should be able to tell you this is going to form 100 stars that have this mass, this mass, this mass, this mass. That we don't know how to do yet. Right? So this is a question, so open research, exactly how many stars of what kind should form for a given gas cloud is a very complex question, because it involves, well, of course it involves simulation, but also it involves complex processes. We need to include magnetic fields. We also need to include the fact that this gas cloud is not just living on its own, it's probably moving within the galaxy, so that you get some sort of Coriolis and shear forces acting on the gas cloud. So it's a very difficult simulation, because even though it's a tiny gas cloud, the fact that it's in a much bigger galaxy can play a role. And then as soon as stars forms, stars will die and will get new explosions, which will affect the gas cloud that we started with. So maybe the second star that will form will be affected by the fact that there was the first star that exploded before. So it's a very, very complex process to understand everything that is going on there. One thing that we know, however, but that's completely from observation, is, and I guess you may have seen this in the lectures, is the so-called chemical Schmidt relation. So what people have done observationally, that you take a galaxy, especially the galaxy disks, because it makes it easier, and you measure the surface density of gas. So this is the amount of gas per units. So you draw a square on a bit of galaxy. You say, what is the density of gas in that square? And so it's the surface density. And then the y-axis is the number of star forms per unit of the square again, per unit area. Okay? And what people have found is that it's not just, if you don't know anything about physics, you could think, well, it could be anything. It could be, there should be no relation. And there is actually quite a nice correlation between the two. So the denser regions form more stars, which probably is not completely unexpected. But the fact that this holds over 4 or 5 order of magnitude is quite interesting. So we know from what that whole process, that whole very complex process should result in. So if you now have a model, if you tell me, I have a model for how stars form from gas clouds, you should be able to reproduce that data, which is very difficult. Okay, so I guess this one is, well, that's not mine, this one's on YouTube, so maybe this one will work. Yes. Okay, so that's a simulation from, okay, I'm gonna describe it first. Okay, and I'm gonna switch off the light. So this one is really cool. Looks really good. So this is exactly one of the simulations I mentioned that are very difficult. Okay, so this is a project from colleagues in the US. It's called StarForge. And so instead of doing full universe simulation or even just one galaxy, they want to do one cloud. They take one cloud, it has some properties, some turbulence, some level of magnetic field or something, and they say, okay, I'm going to simulate it. I'm going to put a really big computer with a lot of details just on that cloud. But the same kind of physics, still only gravity, still gas physics. Okay, you have to add magnetic field. And then something, when a region becomes really, really dense, we're talking almost like, maybe million atoms per cubic centimeter, or something very dense. You can say, okay, here a star is going to form, and then that star is going to have a short life, or short or long life, depending on exactly how big the star is, and then will explode and so on and so forth, right? To give a scale, this is 10 parsec. So we're looking at actually a very small region compared to everything we have talked about before. And then the color is temperature, and the intensity of the color is density. And so one thing which is quite relevant, it also sort of does filaments, right? You can think, but that has nothing to do. This has nothing to do with the dark filament. It's just that forming filament is what gravity does, right? You have a region that's going to just collapse at different rates. And so here the first stars have formed, and when stars form, they start, and when they're very young, they also can have some sort of jets around that. And then of course these jets then, or there might also be some explosions taking place, but once you have this, the gas around that star is going to get suddenly much more hot. And if it's hot, well, it can't collapse under gravity anymore and form more stars. So it's sort of there's a loop there, right? It's blocking, the star formation itself stops more star formation from happening. So now they're just showing us what that cloud looks like from different sides. And you can, again, right? It looks like they're filaments. It's very, very similar kind of structure that we see in the larger scale simulation. And so what these guys are trying to predict is, given different clouds, how many stars of a given mass should form. Shall I play it again? Yes, they like their Star Wars credits. Its class is quite picky at the start. But, no. Yes, if you look up for StarForge on YouTube or on Google, you'll find their movies. I think they have like a 5-minute long 4K version that is really, really cool. So all of these white dots, they're all of the stars that have formed, and so on. Okay, so this is where we are. So we have now formed a bunch of stars. Now you've probably also seen this in your classes. So that is sort of this completely observational. So we know observationally how the stars and the spectral classes, which correspond to temperatures, they also have different luminosities and so on. So that we know from observation. But I guess one of the questions is, do we know how to get there from exactly simulation from the previous slide, right? Do we know how to create all of these different vision of stars? But we can assume that if you're only interested in the galaxies themselves and how galaxies evolve, we can use this as an input. We know what a star should be, so we can say, okay, my model will use this kind of stars everywhere with the right distribution. Now, the key bit about this, so this is, of course, we would like to reproduce what's that. The thing is, most of the stars in there are quite boring. They're like the sun, they do nothing useful for a very, very long time. And especially if you think about all of these processes that drive that. So we saw in the movie before, and also in the one just from the previous one. The first movie I showed you was the whole chunk of the universe, and in the previous movie, that stars explode and do jets and inject energy. Right? Most stars don't do that. Well, they do, but after a very, very long time. So what we are mostly interested in, if you're interested in having an impact on a larger scale, is galaxy stars that explode rapidly, not after tens of billions of years, because we don't have enough time in the history of the universe to get there, and that inject a lot of energy. And that we know, so these are especially some of the brightest stars, then there is this sort of inverse relationship between the mass of a star and how long they will live. Right? So stars that are born with one solar mass, so like the sun, they live for about 10 billion years, so we'll go halfway through with our solar system. The really small stars, they probably live for thousands of millions of years. But that's the majority of the stars. That's pretty useless. Right? It's never going to do anything useful in terms of injecting more energy or anything. But the interesting ones are really the big ones, 60 to 10 to a few solar masses. These are the really big stars. They live for very short time. So if a 60 solar mass star, that only lives for 3 million years. That's shorter than the time of the previous movie. So over the course of this collapse of the cloud, we will get stars that are born and explode and do some damage to their surroundings. So these are the supernova type 2. They're not the one that we use for that distance measurements. A different kind of supernova. They're just massive stars that exhaust all of their nuclear reactions, and then they can't sustain the nuclear reaction anymore. They just collapse under weight and generate a big explosion. One of the key questions that also we don't have a full answer to theoretically is, if you have a gas cloud, how many stars of each of this category are you going to form? Because if you form more of these, then you get more energy fed back into the system. If you form only these small ones, there'll be no energy coming back out of the stars, because none of the stars will actually explode. And the distribution of stars of a given mass is called the initial mass function. So if I give you a gas cloud, what is the initial distribution of stellar mass that we will have? Okay, so what are the products of stellar evolution? I guess I already mentioned that we want to know how much energy comes out of stars. But the other thing that comes out is mass. So the stars lose material over the lifetime, but also they lose metals, which is the astronomy term for anything that is not helium or hydrogen. Do you have a feeling for what the numbers are? How much energy comes out of a supernova explosion? One of the other classic numbers that people always quote. They quote it in very useless units. So the mass, sorry, the energy people. Oh, yeah, this one. So the typical energy of a supernova is 10 to the 51 erg. And erg is 10 to the minus 7 joule, because people like the CGS system in astronomy. So that's a very large number, even if in any system of units. This is you can measure this, right? If people have measured this by looking at, we know where all stars have exploded. You can go back to people measuring or observing star explosion 500 years ago. You can look in documents. Then you can go now where the star is, and you can see a circle expanding of material. And then you can say, well, how much energy do I need to have this explosion and this circle of material going? And you can do that calculation. So that's how we know that number. So like taking historical measurements from a few centuries ago. How much mass does that star lose over its lifetime? Ignoring the one explode. So the ones that explode completely, they lose 99% of the mass. But the rest, like the sun, any idea? That's about half. About half mass over 10 billion years, about half the mass will come out again. So that's a non-negligible fraction. So if you can have formed one solar mass, half of it will come out. So if you take this into account. In terms of metals, oh, well, I don't have any numbers here, but of course they are the only contribution to metal, the only contribution of creating new heavier and heavier elements, especially oxygen. Okay, and finally, this energy goes somewhere, and what we call, so we saw in the detailed cloud simulation that there were jets, but that energy keeps going, these jets keep going, the energy gets pushed away. And then what we call galaxy winds. So what we have here is a galaxy disk, and then what you can't really see here, but that they are, so you can see even in the data here, it will be X-ray data, that there is material going on the sides. Okay. So that is what we were seeing in the first movie I showed, where you have these bubbles coming out. This is this kind of galaxy wind. So that's not just to one star, it's just there are so many stars in the galaxy that are all evolving or exploding or emitting material, but the combined effect is that we are getting galactic winds. Okay, and just before coffee, I'll just mention a couple of things. So the last very key ingredients, right? So I argued at the start, or I argued before that, remember the stellar mass function had this shape which was different from the halo mass function. And I said, in the small galaxies, it's mostly the stellar winds that have an impact. So this kind of processes of stars being born and injecting material is enough, the process to stop more stars from forming. We can think of it this way. If you're living in a small halo, you need less energy to push material out of the halo because the potential well is less deep. Right? So if you have a certain number of stars being born, that should be enough energy to kick stuff out, and it will never come back, it will never form new stars. Okay? It's a bit kind of wavy, but that's at least to first order, is an argument that works quite well. If I make the halo bigger, then at some point I don't have enough energy anymore to kick my gas out. And so that process of stopping star formation by forming stars doesn't work anymore. And so I can explode as many stars as I want, but the gas doesn't go away. And the gas is stuck there and has to do something. That means probably forming more stars, unless something else can come in and do something to stop more stars from forming. And so for a long time it was a puzzle. What can we do here? Why are big galaxies? Why is this show star mass function has this like really truncation shape? Right? Why are big galaxies not even bigger than that compared to the halos? And so people have been thinking about a lot of processes, but one other thing that is observed is that big galaxies also have a big black hole in their center. So this is actually a bit it would be stellar mass, and then the black hole mass here. There's a tight relation, well, tight-ish relation. That this is from observation, and it's almost linear. So I think the Milky Way is down here with a black hole mass of 2 times 10 to the 6, and then you have black hole masses of 10 to the 10 solar masses. So these black holes here, they live in really big galaxies, but the black hole here has about the same mass as the entire stellar mass of the Milky Way. Right? So they are really, really big monsters in these galaxies. Maybe you saw the image from the Event Horizon Telescope 2 years ago, where people observed for the first time black holes. So they observed the one in the Milky Way, which is down here, and M87, which is actually this really big guy up here, which is one of the galaxies in the white holes. Okay, so now that we know that, people are thinking, can we use that fact? Is there any physical processes by which the black holes that we observe in big galaxies could be responsible for this shutting down star formation? And one way you can do this is that by active galactic nuclei. So the idea being that the black hole, of course, we always think of black holes as being something like swallowing everything and like eating everything, right? That is true. Everything that falls to the black hole never comes out. But mostly what happens is that you're going to form again a disk because of angular momentum conservation. That's always the main thing you need to do in astronomy is conserve angular momentum. But you have a hot gas disk around the black hole, and this is very, very hot. And it's also very, very efficient at producing jets of energy. All of the processes there are also very complex. Again, this one involves magnetic field again, but also because we are close to a black hole, actually also involve general relativity. There are very, very complex calculations that need to be done to understand exactly the result. We don't fully understand everything, but we see the observation, right? So we see here, this is a combined three type of thing. So you can't even see the galaxy here, but there's a galaxy in the background. Well, not in the background, it's the same galaxy that is just hidden, it's too small. X-ray is measuring the hot gas. So we see that actually this galaxy here is surrounded by a hot bubble of gas. And we think that this hot bubble of gas has been generated by the black hole generating these jets and heating the gas at large distances. And why does that stop star formation? If I'm embedded in a very hot gas halo, then I can't get new gas coming in to form more stars. So that would be the idea. And also by injecting a lot of very high temperature gas close to the galaxy or in the galaxy, that also stops star formation. Because if the gas is too hot, it cannot collapse under its own weight anymore and form new stars. And so in the simulation, we can also do this. We can also do AGN jets. So we can simulate the galaxy and do jets and see that whether this kind of processes actually work. So if I come back to this, that's what I mentioned before. So if in small galaxies, stars that just regulate themselves by forming enough stars, they inject enough energy to stop more stars from forming. So to be there, if you want to be a star in a small galaxy, you have to be there early, be one of the first stars, or you will just never be born. And in the bigger galaxies, what happens that, right? And then so that process goes on, and until when you reach here, then your halo is so big that you can't, stars themselves are not efficient anymore at forming, at stopping more stars from forming. And that's also the mass where we start observing more and more black holes inside galaxies, supermassive ones. And so we think that from here on, the supermassive black hole sort of takes over, and it's the one that does the regulation business and stops more stars from appearing. So the black hole grows because it's accreting stuff, but while doing so, there's also a lot of energy being injected and stop more stars from forming. And that's why we get this exponential cutoff. And finally, one process I haven't mentioned is also that I mentioned this merger with the stars. But one thing that can disturb the whole story, so you have a nice galaxy disk, it's been just doing its own business for a long time. And suddenly there's a small galaxy coming in with a lot of fresh gas, and that's suddenly going to create a new burst. Or new,
I have a question with the last slide.
Yeah.
So I understand the fact that in the bigger galaxy, the efficiency is low.
Yeah.
But I'm looking at where our galaxy is pretty big, right? Am I correct? So
Around here?
Okay, so we're there, but it's necessary, it's like, is there right way that if you have a bigger galaxy with a massive black hole, that black hole will be a AGN or not necessarily?
So if you look in observations, so it's very difficult to measure the black holes themselves. The ones we see, so the ones which are nearby galaxies, we can feed them through some of their effects directly. But the ones that are further away, we only see them if they are doing something. You can think of quasars, for instance, or all kinds of other radio galaxies jets. So we can only observe black holes, because of course they are dark, and so we only observe them in the process of doing something. But so now you can ask the question: does every galaxy have one? Probably. Then you can ask the question: what is the fraction of the time that the black hole is doing something? Because that would be important for you. Well, if your black hole is only doing something 1% of the time or 99% of the time, that would be a difference in the injection energy, the rate of energy injection. So there can be many different there are many things we don't understand entirely. But if you take guidance from simulation, we know this has to happen, but the exact details of how it happens, we don't know for sure. Okay? Okay, so things that I've not covered, that will be the remaining 6 months of lecture information. And things like quasars just mentioned, but like starburst, what happens if suddenly some galaxies suddenly start forming a lot more stars? That could either be because there's a galaxy merger, or sometimes because somehow the disk got perturbed by different effects. How do we form dust? We observe the dust line in galaxies. Magnetic fields. How do we? So we saw how we can form a disk just simply by cooling and conservation of thermal. How do we form a bar? You see, galaxies have bars, many of them. How do we get there? What do we do for that? We didn't talk about galaxy shapes. We showed how we can make a disk, but they're all elliptical galaxies. So one easy process is to crash galaxies with each other. Right? And we said this merged disk, galaxies grow by merging with each other. So that seems like a natural way, but it's not, maybe not the only way. Because we also see dwarf galaxies that have an elliptical shape. So how did these guys form in the first place? Galaxy colors, environment effect. If you take the same galaxy, but instead of being alone in an empty region of the universe, you put it inside a cluster, it will not behave in the same way. And one way to think about it is because there's more gas in the play, or the potential well is different, so surely that must have consequences. We call this environmental effect. Cosmic rays, we charge particles that are emitted by stars, or by supernova, or by black holes, that probably also have an impact. This is very poorly understood. We don't know what exact impact of this is. If you ask some people with some simulation will say, this is the most important thing there is, all the rest is completely irrelevant. And some other people will say, it has no impact whatsoever. So we don't know. And then there are many other things that, that are sort of very actively being researched. Any questions? If not, we get a coffee break. Or even if you have questions, there'll still be a coffee break. Tomorrow, right? Sounds good. Yeah. Are you going to the airport here, or are you going just after the session, or like? Just after the session, I'll just follow you.
Well, follow me.
Going in the direction, okay. You can come and give a talk. Perfect. Yeah. You have a question? Yes.
What AGN is that?
Oh, active galactic nucleus.
And I would say that the majority of the galaxies are because efficient galaxies are around 10 to
Yes.
Yeah, no.
The 12.
And most of the halos are 10 T.
So
The universe is big.
I like the way you think. I like the way you think, but it's not quite correct. So it depends what you mean by most galaxies. So most of the stellar mass in the universe is in galaxies of 10 to the 12. But if you say, is it most of the galaxies? It is not the case, because there are many more small galaxies, but they don't contribute much mass. So it depends if you want to count by mass or by galaxy. Right? There are many more dwarf galaxies, like maybe 1,000 times more. Well, maybe not, maybe 100 times more, but they contribute each only 0.1% of the total. So if you multiply, it's only 10% or something. So it's not much. But if you take any random star in the universe, and you ask, what halo mass we live in, what is the probability, what is the most likely halo mass that that star lives in, it's going to be in a 10 to the 12 solar mass scale. If you ask what is the most likely galaxy that it lives in, it's going to be dwarf galaxy. There are more dwarf galaxies than right?
Next.
Yes.
Of the information depends only on the halo mass.
Well, that was also a big question. That we don't know. So we won't. So we see supermassive black holes in big galaxies. There are some claims that the reason that people have big black holes in dwarf galaxies. Whether they are doing a lot of action, we don't know. So it's also not. So we don't think that suddenly when the galaxy becomes very big, suddenly the black holes form. So the question is, where did the black holes come from in the first place, and how did they get that big? So there we don't exactly know, but it could be that totally every you can. So one model would be to say at very early time. If I go to redshift 20 or 30, we know that the stars that are, so at that point we only have hydrogen and helium. So these will form stars that are very different from what we have now. They have called population level stars that look very, or even zero intensity stars. And so there, we think that they can be much bigger. They can be stars, the stars themselves, right? And because they're much bigger, they're also going to potentially directly they're going to collapse into a black hole. There are 4 relatively big black holes already at early, maybe 100 or 2 or 500 solar masses black hole. Okay? There's also some models where the matter just collapses and collapses and collapses. Instead of forming a star, it directly forms a black hole. It would be a direct collapse black hole. That would be different scenarios. And so that's at early on we form in many small halos. And then because the halos merge, the black holes will merge, and then it also eats more and more gas around it. And if you're in a very big galaxy, also in big halos, you already form from many small halos. And that would be a way how you get to a black hole which is big enough that it starts doing something. Exactly how that works, you don't know. Black hole merging definitely plays a big role. What is the starting point? We don't exactly know.
I have another question. Once again for the galaxy keeps growing.
Yes.
Always. Forever.
So what we see if we take what we can measure the star formation in the galaxy. If you take a really big galaxy, they have a small star formation. So the same galaxies are they don't form it's not big. They always be a small galaxy. So small.
Lo de la acción.
Acción, pero que no se le da perfecto.
Pues demostrar ese P más ese
Esta.
No.
demostrar la
De eso, llegar a la situación de más. Llegar a la situación de más. ¿Qué le parece?
Pero esa la puso de sur. Esa la puso de Sí, no pone.
Al final sí se comprobó. Ya hizo la prueba técnica.
Es una acción para sacar la fuerza y la fuerza, la acción para demostrar su varianza que conduce a la ley de energía, la relación de exposición y
¿Qué?
Sí.
Sí, yo ves que.
acción para sacar la fuerza y la fuerza, acción para demostrar que su invarianza conduce
Los
a
verán que
Sí, vale.
sí, eso es.
No, no, no.
Siempre discusión de una onda magnética, la relación de discusión de una onda magnética.
O sea, esa.
Usando exclusivamente la notación. La notación.
O sea, el indicador de U.
Por el
Entonces sale con
in German.
I can lecture, probably, I can lecture in French. Okay, so we talked a bit about the main bits of very broad brush galaxy formation theory. Of course, there's a lot more going on. I just want to say a few things about how we could simulate all of this, right? So we saw very simple physics. We got to make a galaxy disk, or at least, sorry, a gas disk. And so, can we go beyond that? What do we do to make the kind of movies we have seen before? So, we've already looked a bit at that. So, we will simulate a lambda CDM universe. So, we know the starting point from CMB observations. Someone asked the other day about boundary conditions, and we got the answer that we should use Purdy boundary conditions, so we don't have a problem at the edge. What are the forces? Well, gravity, hydrodynamics, maybe magnetic fields, maybe radial transfer. Radial transfer is the technical term for the interaction of photons with gas or propagation of photons. Cosmic rays. And then there are different pieces for the different bits of matter we like to add to our simulation. Dark energy, 70% of the total, but that's the easiest thing. It's a one line of code because all darkening does is just rescale the universe. So that's like the simplest part. You have done 70% of the work with basically one line of code. Dark matter, we talked about it on Tuesday. It's just gravity, right? Dark matter, cold dark matter just behaves gravitationally. Normal matter, gas, we talked about yesterday. So we treat it as an ideal gas, compressible ideal gas, for instance, using SPH. And then everything else, which is where it becomes interesting, stars, black holes, maybe neutrino particles, the dust, planets, anything, that we're not going to solve directly. We're going to treat it what we call subgrid models. So what is that? So just coming back, maybe one study for green subgrid model, is just to give you a sense of the scale of the problem we have, right? So I showed you this movie at the start where we had this white bubble expanding. And I was arguing this is the hot gas around the big galaxies. So this is now real data. This is the M87 galaxy, center of the Virgo cluster, not far from where we are. And that's one of these bubbles that we can see in X-ray. And that's about megaparsec. So we see this data. So it's good that the simulation do this as well. Now, what is creating such a bubble? Well, frankly, I was arguing before by the AGN activity. So for instance, in the same a lot, we can see a big radio jet. Like in radio emission, we can see a very big jet coming from the center. Now the scale of this image, times smaller than this one. Okay, and I've zoomed in a lot. And at the center here, so here the center, the white dot is the galaxy. At the center of that galaxy, there's a big supermassive black hole, which the Event Horizon Telescope observed, I think 2 or 3 years ago. And that's the image they have. And that's essentially, you can think the warping of the photons around the black hole in the center. And that is now 1 million times smaller than that. Okay. So maybe I can simulate this, because I have enough particles in my simulation to do this. But there's here something which is 1 billion times smaller. And when that disk fluctuates on an hour-by-hour basis, it creates jets. And these jets heat up the gas. Right? That is so small that we'll never ever be able to simulate the whole thing. If I'm going from here to here, it's impossible. It's never going to happen. At least not until we all retire. Right? Computers will be so big and it's way too complicated. So the idea is to say there are bits we're going to simulate directly, and bits where we're going to have to invent some recipes to make for the missing bits of physics. Right? So in summary, simulations do not have the resolution to take all processes. What we do is that we change strategy and we put models of what happens below that scale. And here we're talking about particles, but if you think about the grid simulation, you could imagine what happens within each cell of your simulation. You say, oh, here's very dense, so a black hole was born, and something will happen. And because it's usually based on grid, it's happening below the grid, so below the size of the grid, and people call this below the grid models or subgrid models. And then the key difference here is that these models are not based on differential equations. So we started for gravity and for hydrodynamics. Here are my differential equations. I'm going to find a computer approximation to these equations. And I know that if I do this properly, it's going to converge and give me the right answer. Here, for most of these things, I do not have a differential equation that I know how to solve. I will have a model that I sort of build by hand for what should be happening in these regions. Okay, so I can give you some example. I'm going to give you just one starting example to show you how difficult that is. So this is a paper from 2012. And what they did here is they asked 12 different groups that do simulation of galaxies to simulate the same galaxy. So they say, here is a halo, or here's a bit of initial condition that is going to form a halo, which we think is going to be like the Milky Way. Run your model and tell us what galaxy you get. Okay? It's the same halo, so ideally, we should all get the same answer, more or less. So what you have here on the x-axis is the stellar mass, and this here is the rotation speed, so the rotation speed of the galaxy disk. If it's a disk, it's not even clear that all of them are disks. And all of these are different results from the different groups. So they disagree by a factor of 10 in what is the mass of the galaxy that will form that halo, and by a factor of 3 in how fast that disk is rotating. So it's a very difficult problem. Also, we don't know what the real answer is, because we don't know what in nature what that specific halo would have done anyway. But we know in the data here the black points where we expect galaxies to live, these observations. So hopefully, ideally, these points, even though we don't know which point it should be, but they should ideally be within that cloud of points. So that's a very difficult problem. That was 10 years ago. Things have improved a bit, but we're still doing these kind of comparisons. So here's a more recent one from 2021, I think. Again, here's now 7 teams simulating the same region. And here, I'm not even showing you any quantitative plots, it's just maps where people use exactly the same color for the same temperature, the same density. And you can see visually, even before doing any quantitative analysis, that we do not agree for a given halo what galaxies should form in there. It's still a very complex problem. As a community, we haven't yet converged on an answer we're all happy with. And if you look at it more closely, we can look at it later, but the bottom one is just the stars, the shape and everything looks very different. It's a very difficult problem. Nevertheless, we can try to do something. It's not hopeless. So there are many galaxy formation models. Just showing you. You may have seen some of these names if you have read papers in the last few years about models that people use for simulation. So I'll show you many simulations from our group which use this Eagle model. There is this illustrious TNG is another very popular model that people use a lot for different models. Different models, so this is they also work at different resolutions. Different groups are interested in different level of details. Some people are interested in doing a lot of galaxies, a whole population, so they will use maybe a lower resolution because then they get more galaxies in the same computer size. And some group, maybe they prefer to say, we're going to do a very small region, but a lot of detail. And then that also fits in the big computer. And so there's a whole zoo of things. If you're using the Swift code, which I've been using so far, we have 3 different models in there that cover 3 different regimes, so that's quite cool. We can do comparison even within the same setup. And I think, well, not I think, I'm sure this afternoon we're going to be running a small simulation using this Eagle-like model to make galaxies. Okay, so I mentioned this resolution problem before, that I will never be able to simulate both full halo and the black hole in the center. It's even worse than that. Even before reaching these scales, we can have a problem. So what I'm showing here is I'm taking all of the gas in my simulation. The first one I showed is red, moving very red. I take all of the gas in that simulation, and what I'm plotting here is the density, so that's in atoms per cubic centimeter, and the temperature on the y-axis. And there is all blob here. And so what we do in this model is that we impose a resolution limit. And why do we do this? If you have something which is cold and dense, it's going to collapse. It's going to get denser and denser and denser until it forms stars. But if you want to get denser and denser, it means you're going to smaller and smaller and smaller and smaller scales, which means you need to make a simulation high and high and higher resolution, which means you need a bigger computer or more time, or it gets really, really complicated. Okay? So what we choose to do, and what many other models also choose to do, is to say, I can't go there. I don't have enough computing power to go in that regime, so I'm going to artificially put a line here and say, I'm not letting the gas go down there. Which is wrong, it should go there, but if some gas starts to cool down here or gets denser in some ways, I just add some energy to it, I heat it up or do something to it, I cheat a bit, to prevent it to go below that line. So that bit here is simulated completely naturally and solving the correct equations. It's just around here, I'm saying this is my limit. I can't go beyond that, okay? And that would be saying this is about a resolution limit of 1 kiloparsec. I'm saying I'm not allowed to look at things below 1 kiloparsec. So the size of the Milky Way galaxy is how many kiloparsec?
5 kiloparsec, I think, the Milky Way. Or you mean the whole, including the halo?
Well, then in both cases your answer is wrong. So the Milky Way disk is about 20 kiloparsec in diameter, and the whole halo would be 200. Okay? The sun is 8 kiloparsec away from the center. That's maybe another number that's good to keep in mind, to give an idea. So here we would say, we can't look at the details within the galaxy, but we can look at least some details with 1 kiloparsec resolution. What is the problem here? Is that here is where everything happens. This is where stars form. This is where the cold gas is. This is where dust is. This is where stars explode. And we're not doing any of it. Which means that in our model here, we're doing this part here, which is just hot gas physics, but all of the actual action we'll have to do it not directly solving differential equations, but via some models for what is going on. Now, I showed you before the movie of a single gas cloud forming stars. They are simulating only that region and they're doing it directly. So they put all of their computing power just into doing that part correctly, but they don't have the rest. It's a choice to solve one problem or another problem. So what are the processes that you need to include? Exactly the process I mentioned before. You need to include the cooling of gas, the star formation, the fact that stars explode and inject material, they inject mass, they inject elements. The black holes are born, the black holes accrete material, the black holes inject energy. That's all what we add to our model. That was all in the bottom right region that I'm not simulating directly. So, sometimes you see people say, well, look, this is your subgrid system. I just twisted the original wording here, and then people will say, well, if it doesn't work in the first place, all you do is just like change a bit of the numbers, it's going to work again, and we haven't learned anything. And that is not entirely wrong, it's also not true. It's true that we don't understand all of the details, and I showed you before that different groups that have each their own pile of whatever dirty stuff they do, we all get a different answer, right? But that doesn't mean we're not learning anything, right? I'm trying to convince you of that in a second, so I'm going to say big no, this is not true. There's a lot we can learn from these models. And I'll give you an example. So there is a weather forecast from the region, right? Now, when people do the weather forecast, they run simulations. Typically what they do, it's fluid dynamics. They don't do just SDH, they use grid-based simulation because the resolution is very fixed. And typically, normally they use about a kilometer size cell. Right? So they will have a grid over all of Colombia, I suppose. And then they just discretize it in cells of 1 kilometer. And then they calculate the derivatives between these and exchange the gas, the air, the amount of rain, whatever is exchanged between the cells using differential equations. But that's a 1 kilometer scale. Clearly, if you are looking at raindrops are 1 millimeter in size. So these people that do the simulations are also cheating, but I'm arguing it's not cheating, they're just using a similar spirit. Right? You are using a model for what happens, you don't care about every single raindrop, you don't need to simulate every raindrop to tell you that there's a cloud here, there's rain. All you need is a good model that tells you if in this cell here it's, I don't know, very turbulent or the temperature is dropping very quickly, a cloud will form and rain will fall. I don't have to simulate every single drop. And it sort of works. We get decent prediction. I don't know whether here, if you're confident about the weather forecast, it seems to be raining at random times, but I don't know if you trust the weather forecasting system, but usually it works quite well. We know the simulations, they are based on also some of these subgrid models, and they give us this answer. They tell us when a storm will happen and so on. Right? So we're doing the same thing. And here, that's a ratio of 1 million. I mentioned before with my plot saying we have a 1 kiloparsec limit, or actually this simulation uses the particle mass of 1 million solar masses. So if I were to say the ratio between 1 million solar masses and the mass of the sun, which maybe we care about as a good scale for simulation, that's also a ratio of 1 million. So this kind of things is doing the same sort of business of having small models inside each cell for what is happening, and it works. Right? So we're trying to do the same thing. And it's not just weather forecast, it's a very normal business. So here's an example of what you can do. So I said before, we cannot simulate every single star forming. It's too complicated, and we don't have the resolution. One thing we can do is use the data. I showed you this plot before. We know from observation something about the Kenny-Kirchner information. So what I can do in my simulation, I can measure the density of a region of gas, and I say, I assume this is true. Right? It's true, just take this in, and if you tell me that the density of my gas is this, I read it here, and I say, okay, then in this gas blob, I should be forming this many stars. So that's a model. You can say I don't understand we don't understand the physics of what is happening here in detail, but I can use this as a model, and by construction, I'm going to form a decent number of stars, correct number of stars in my galaxies. Okay? So, the good thing here, well, we get that out of the simulation by construction, but the bad thing is, I can't tell you why this works. That simulation that is using this as an input cannot tell you why this relation happens in nature in the first place. But if you want to know that, then that's not the right kind of simulation. You should do this other type of star forge-like simulation where you simulate a single planet. If you're interested in the whole galaxy, using this as part of your model is fine. And you're just putting in to get the right amount of stars from the right place. Okay, so I'll read this off. In the simulation the other day, we can measure the density of gas everywhere with the particles. We know how to do this. This is mass times W, what that enters the equation. It tells me how many stars should be forming in that same region. Same thing for stars, a bit more complex, but same processes, right? We now have stars, and again, I can take results from observations. We know how many stars of different masses are born, so I can use this as an input for my model. And also know from observation how long, and also apart from theory, how long stars of different masses will live for. And we argued before that when stars die, they inject 10 to the 51 ergs of energy. So I can use this as an input. I can construct a model that will inject that. So I have a region where stars are born, and I say when the stars have reached the end of their life, I'm going to remove the star from the simulation, but I'm going to replace it with this amount of heat at that point. And that should be doing the business. Okay, so we don't simulate the stars. Then there are some complexities because it's an approximation, so maybe some energy will be lost, maybe the resolution is not good enough. Should we inject energy via temperature, or should we create momentum? Right? These are different approaches. It should be the same amount of energy, but it probably will have a different effect on the gas if you kick the particle, if you push them away, or if you just keep the gas. Maybe there's a bit of both. So that poses all kinds of questions, and so this is the part where this pile of unknown things that you have to shake around to get a good answer. This is where it becomes a bit more like that, because here we don't know what should be the right answer, and it will probably depend on. It will also depend on whether you're doing a simulation with particles or with a grid or with a moving mesh, because some of these details can affect the exact implementation of the details of how you want to do this to make it work perfectly. But at the same time, we don't know very much about supernova anyway. We don't know whether they depend on, whether the energy depends on redshift. Should not, hopefully not. But it depends on metallicity. How many stars are born of a given mass, we're not going to be sure. And what about binary stars, triplets of stars, and so on? That will also change the amount of energy. All of this we don't know anyway. So the fact that there is uncertainty even here means that the fact that we don't exactly know how to do it in the simulation itself, sort of at the same level of uncertainty. But in any case, that means there are some free parameters. So I can tweak things up and down. Maybe to make my simulation work, I shouldn't use 10 to the 51, but I should use 1.1 times 10 to the 51, because somehow when I put the energy in my simulation, the bits gets lost because of numerical approximations. So there are some free parameters. And so what people end up doing, maybe that will work or not, is that we play around. So we looked at this plot before, the stellar mass. Right? How many galaxies of a given mass exist in a region of the universe? And this will be the stellar mass versus the size of the galaxy, so how extended this is. And then the orange points are data, and the blue line are simulations. And what we do here is, because we have these parameters that we don't know the value of, you can say, well, I'm going to stir the pile and find the good value of parameters that will give me something reasonable. Of course, if my parameters get completely ridiculous, then I probably have a problem and I have to go back and design again. Let's see whether that works. No, okay. I'm just going to show you that if I vary the parameters, I can get all kinds of different answers where these lines move around, and then you can start trying to optimize. You can do some sort of Monte Carlo technique or try to find the best value of the parameters for your model in some sort of automated way. Anyway, just to finish off, saying that it works. So these are some results that people from different groups. So I showed you there, if we all try to simulate the same halo, we don't always agree. But if you ask here's a million halos from all different galaxy population, then we sort of still have decent answers, because then if one halo gets slightly higher mass in one model, maybe it gets slightly less lower mass in another model, and then it sort of averages out. So these days people can get the correct with the number of the stellar mass in per unit volume. I don't know, they can get the colors of the galaxies, they can get this is some limiter things, they can get the rotation speed versus stellar mass also quite well, and so on. So there are many results that models based on these sort of approximations can get right. Which is, I don't know if it's a good or a bad thing, because it's a good thing because we can make galaxy population right, but also they're based on models where we don't necessarily understand all the details in it. Although that does still tell us something about what are the allowed processes. For instance, if I have a model where I don't have AGN at all, because then I never get that right. I can tweak my parameters as much as I want of the rest of the model, I will never get this part of it. I get my stellar mass function to keep going for it. I don't get this exponential break. So we're still learning something, even though we have thing, right? And there are other processes that will affect, for instance, the rotation speed. If I only make all of my galaxies, none of them are disks, then they will never get the correct rotation speed. It will all end up being really dense blob. And there's nothing I can do with my parameters, and so there are some exploration we can do to learn about this process. Other thing we do is that we can make cool images, which is can be quite fun. I don't know if we can yet completely trick observers, but give them a fake image so they can recognize that it's from a simulation. I think some of them look pretty good, especially if you start adding fake stars in front to trick things that say, oh yeah, this is really from a fake observation. Or like sometimes people also add like broken pixels or something. Say, oh yeah, this telescope has a broken pixel here, so it makes it more realistic. But that's also quite useful, right? Because okay, we can compare the simulation to like the stellar mass, but people don't measure stellar mass. They measure light in different filters, right? So, and then they have a model, observational community will have a model to say, if I observe light in all of these bands, then it will correspond to this given mass. But maybe that model that is used is not quite correct. So taking the simulation and making images that then can be observed using the same exact approximation that people in observation do can be quite useful, because then you're comparing exactly the same. You're doing the same exact comparison, not just comparing pure theory with pure observation. You're trying to bring the two very close, so you're not making any mistakes. And I was going to end up here with the movie we saw on Monday, but because the internet is playing, I don't know if I have this one. Just to finish on that. No, I don't. If it's on YouTube, it will work. Anyway, I think it's not going to work. But let's hope anyway. Anyway, we saw it on Monday already. Just to finish off saying that, in principle, if I put all of these ingredients together, I can get something that looks like a decent set of galaxies, not just in the data points, but also just visually as a population in a region of universe. Okay, so tutorial for this afternoon. What we're going to be doing is we're going to take the same code, but this time we're going to switch on some of the galaxy formation bits. So far we have only run with gravity or with hydrodynamics. Today we're going to run with both together, but also switch on one of these galaxy formation models. So meaning that we include doing some cooling due to the gas, some star formation model, which is actually based exactly on that relation I showed before, so it's using exactly that approximation, and also some star and black hole model. We're going to run a very small region, otherwise it might take far too long. We're going to run a small region of the universe for a bit, and the script will have ways of doing some simple analysis. And then the other thing we can do from this simulation, and it's also a diagnostic we can use, is to plot the star formation history of the universe. I don't know if you have ever seen that plot before, but what you can do is you can take a whole region of the universe and say, what is the number of stars formed per unit volume of the universe? And so with the x-axis here. So stellar masses per year per megaparsec cube, and as a function of time. And we see is that in the data is that at around redshift 2, the the universe was forming a lot more stars per unit time than it does now. So it starts with a big bang down here, goes up, and then for the last 10 billion years, so since Redshift 2, this rate of forming stars has been going down and down in the universe. Part of it is due to lambda, but not all. So that plot we can try to make this afternoon from small simulation. And I think we'll stop here for this quarter. So I'll see you after lunch.
Yes.